Hello guys, welcome back to another NMR spectroscopy lecture. Today we are going to be looking at how to determine the number of signals produced in NMR spectroscopy. Okay, let's take a look at this example. We have CH3, CH2, CH2, and Br. Okay, so what will be the number of proton signal produced from these molecule? So if you, let's take a look at this first carbon here. If you have this structure like this, hydrogen, hydrogen, and hydrogen. Now if you can see that these three hydrogens are attached to the same carbon, which means that they're having the same they're in the same chemical environment, then basically these three hydrogens will appear as one signal. Okay, now in a nutshell, all hydrogens that are attached to a particular carbon will appear as one signal, or usually appear as one signal. Okay, so in this case here we have one signal here. Let's call it signal A. Okay, and here we have CH2. We have two hydrogens attached to this carbon, and they will also appear as one signal. Okay, signal B. And the last one here, we have two hydrogens as well attached to one carbon, and the two hydrogens are in the same chemical environment. They will also appear as one signal. So we have signal C. So in these molecules, we're going to have three signals produced in the NMR spectroscopy. That's three proton signals. Okay, three proton signals produced. Let's take a look at another example. Now let's look at this molecule. How many proton signals do you think it will produce from this molecule? I want you to pause the video and give it a try. Okay, so now before you're able to do this particular one, you might want to consider what they call line of symmetry. Now there's some molecules that has what they call the line of symmetry, which means that they can be divided into two, okay, and two equal parts. This part is the same as this part, okay, so which means that this side basically are in the same chemical environment as this side. Okay, this methyl group is the same as this methyl group here because of this line of symmetry. So you should always take note of line of symmetry. Always consider that whenever you see any molecule, okay, to ensure that you get the correct signal, number of signal. All right, so now we have CH3, three hydrogens attached to this carbon, and these three hydrogens will appear as one signal. So let's call that signal A here, and this methyl group here is the same as the methyl group here, so which means this also will appear as signal A. The hydrogen attached to CH2 will appear as a separate signal because they are different, so we have, let's call it B. So how many signals are we going to get from here? We have total of 2 hydrogen signal. Okay, let's look at another example. Okay, so let's look at this example here. Pause the video and give it a try. Okay, so looking at this compound here, you can tell that there should be a line of symmetry here, right? If there's a line of symmetry here that divides this molecule into two equal parts, right? So which means that the signal here on this side will be the same as the signal on the side. Okay, so this is, if the signal is A, this signal also will be A. So from this molecule, we're going to have just one proton signal. Okay, let's take a look at another example. So let's look at this molecule. How many proton signals is it going to produce in NMR spectroscopy? Pause the video and give it a try. As you can see, there is no line of symmetry. Okay, there is no line of symmetry. And let's start from this carbon here. You have this carbon here. This carbon has CH3 attached to it. Yes, how many CH3? That's 3 CH3. 1, 2, 3. So this basically is what is a tertiary um, carbon, right? It's a tertiary carbon. All right. Now all these CH3 attached to this carbon, they are in the same chemical environment. Okay. So all the CH3 are in the same chemical environment. Basically, this hydrogen here will produce one signal. So here we're going to have one signal here, A, and A. Okay, because they're in the same chemical environment, they are attached to the same carbon. And let's look at this other CH2 here. The CH2 here is different, so we're going to call it signal B. And let's look at this other CH2. Now this CH2 is different from this CH2 because this CH2 is closer to just CH3, just a methyl group, but this CH2 here is closer to a tertiary carbon. So they are in different chemical environments. They're going to have different signal. So this CH2, the hydrogen here will have signal C, while the methyl here we have a different signal as well because it's in different chemical environment. We call that signal D. So how many signal is it going to be? 1, 2, 3, 4. We're going to have 4 hydrogen signal, 4 proton signal. Okay. So let's look at another example with line structure. Okay. Let's use line structure. Let's say we have this structure. This is 3-chloropentane. Okay. Now, how many proton signal would this molecule give in NMR spectroscopy? I want you to pause the video and give it a try. So the first thing to do is to check if there will be a line of symmetry, and in this case there is a line of symmetry that divides this molecule into 2 equal parts. So this side is the same as this side, which means they are in the same chemical environment, right? So here is CH3, right? Here is CH3, and here we're going to have one signal here. Let's call it A, and this CH3 also is the same as the CH3 on this side. This also will be the same signal A, right? And here we have CH2 here, right? And this CH2 we have a signal B, and this CH2 here is also the same as the CH2 here. This also will be signal B. Now here we have hydrogen on this side. We have hydrogen here, and this hydrogen is in different chemical environment from the rest of them, and that will give us signal C. Okay, so now how many proton signal do we have here? 1, 2, 3. So we have total of 3 proton signal. So I want to try this one, 2-methyl pentane. How many proton signal will it produce in NMR spectroscopy? So, like I said, the first thing to do is to check if there is line of symmetry. And as you can see here, there is no line of symmetry here. Right? So here we have CH3. Here we have CH3 here, right? And here we also have CH3, and this you have CH3 here, we have CH3 here. This CH3 are attached to the same carbon here, right? So it means that this there will be a signal here, A, will also be same as the signal here, A, because they are attached to the same carbon. right? Now let's look at here. We have one more hydrogen here, right? We have one more hydrogen here. So this hydrogen is in different chemical environment. It will appear as signal B. And here we have two hydrogens, right? You have two hydrogens attached to the same carbon. They will all appear as the same signal, as one signal, and we call that signal C. And here also we have two hydrogens here attached to the same carbon, and they are in different chemical environments from the rest of them, and there will be signal D. And here we have CH3, okay, that is different from the rest of the CH3, and the signal will appear as one, and we call that signal E. So how many signals do we have here? 1, 2, 3, 4, 5. Here we have a total of 5 proton signals. Let's just look at another structure. So we have this. Now, how many proton signal we produce from this molecule? Okay, I want you to try this one as well. Pause the video and give it a try. So now the first thing to do is to check if there is line of symmetry. And as you can see, there is a possible line of symmetry that can divide this into two equal parts like this. So as you can see, this side is the same as this side. All right. So now let's look at, here we have CH3 attached here, right? Here we also have CH3 attached here. So here we have a signal A. We also have a signal A here, right? Now, since this side is equivalent or equal to this side, the same as this side, also here we have CH3, CH3. This also will be signal A and signal A here as well. And here we have hydrogen here. Don't forget, you have hydrogen here. This hydrogen is different from the rest of the hydrogens here, so we call it signal B. And it means that here also we're going to have a hydrogen here as well. And since this side is equal to this side, here also will be called signal B. The signal here also will be signal B. And let's look at this side here. You have the CH2 here. You have two hydrogens. Okay, the two hydrogens are attached to the same carbon, so they are the same. They're in the same environment. They will appear as one signal. We call that signal C. And since this side is same as this side, here also we have hydrogen. So this also will appear as signal C. All right. So now, how many proton signals will this molecule give in NMR spectroscopy? We have A, B, C, which means we have a total of 3 signals, proton signals. I hope that's clear. So let's look at this structure. We're going to determine two things here. We're going to determine the number of proton signal and also the number of carbon signals that will be produced. Okay, so I want to give it a try. Pause the video and give it a try if you can. Now, so the first thing to do is to check if there is a line of symmetry. And as you can see here, there is no possible line of symmetry, right? And here we have CH3. Here we have CH3, right? So this CH3 and this are attached to the same carbon here, so they'll appear as one signal. Let's call it signal A and signal A as well. And here we have hydrogen here, right? And which is different from other hydrogens. We call that signal, it will appear as signal B. And here we have two hydrogens, right? and they are different from others. They will appear as signal C. Here we have CH3, CH3, and CH3. Okay, so they are both they are all attached to this center carbon here, and which means they are in the same chemical environment. So we're going to call them signal D, 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 and D as well. So in total, how many proton signal would this structure give? We have A, B, C, D. That is a total of 4 signal. Now, what about carbon signal? Okay, how many carbon signal will this structure produce in NMR? At signal A, we have a carbon. Okay, we have a carbon A, signal A. Also, here also the same carbon, signal A. B here also we have carbon here, signal B. Remember, blue is for the carbon, white is for the hydrogen signal. Now, so at this side also we have a carbon here, C, and here we also have carbon D, which are the same, D and D, which are the same. But here we have carbon as well, because even though there is no hydrogen here, there is a carbon here, right? So this carbon will appear as signal E. Right, so in the carbon NMR spectrum, we're going to have a 5 signal. Okay. So let's look at this benzene structure. How many proton signal is it going to produce in NMR spectroscopy? Okay. So now let's not forget this benzene structure has hydrogen. We have hydrogens attached here, here, here. Right? All the hydrogens here are in the same chemical environment because each of them has one hydrogen beside them. Okay, to the left and also to the right. So basically, all the signals here will appear as one. So we have one signal here, A. So in benzene, we're going to have one proton signal or one hydrogen signal. So let's look at another one. What if we have this structure here, chlorobenzene? How many proton signal will it produce in NMR spectrum? Okay, so the first thing to do is to check if there will be a line of symmetry. As you can see here, there is a line of symmetry. So if you draw this line of symmetry here, this side is equivalent to this, or is the same as this side. They're in the same chemical environment. Okay, now here we have hydrogen here. We're going to have a signal here, A. Now here, are we going to have the same signal here, A, or what? What do you think? Now this signal here will be different from this signal here. Now the reason is this signal will be, this hydrogen here is closer to a chlorine, but the hydrogen here is closer to just hydrogen. So which means they are in different chemical environments, and hence will produce different signal. So we have A and B. Okay, now since this side is the same as this side, here also we're going to have signal B, and here we're going to have signal A. Okay, and here we're going to have a signal here, and this signal is signal C. Okay, and so in total, how many signals would this chlorobenzene produce? A, B, C. So we're going to have a total of 3 hydrogen signals. So what about in carbon NMR spectrum? How many signals will this structure produce? Okay, so we have carbon here. Okay, we have a carbon here. So basically we're going to have 4 carbon signal. This carbon here remains the same. Carbon A and A are the same. The first one, B here also, they're the same. And we have C here. Then we have D here. Rather, this is D, not C. This is D. So this will give us 4 carbon signals. Let's take a look at this structure here. Paraxylene. We are going to look at both the NMR signal and the carbon NMR signal. All right. Now, looking at this structure, it appears there is a line of symmetry. Okay. So this side is equivalent to this side. Now this H3 here has a signal, and we call that a signal. Let's call it signal A. And since this side is the same as this side, this also will be signal A. Right? Now look at this. Let's look at these other hydrogens here. We have hydrogen here. We have here. We have here, and we have here. Right? Now this hydrogen here is closer to methyl group on this side, right? And it's closer to hydrogen on this side, right? So this, let's call this signal B. If this is signal B, this also will be signal B, right? So now this side also is closer to methyl group. This hydrogen here is closer to methyl group on this side, and the other side is also closer to a hydrogen group. So basically, all these will appear as one signal, signal B, and also here will also be signal B. Okay, and so how many signal are we going to have here? NMR signal we're going to have. We're going to have A and B, which means we're going to have 2 signals for the NMR. And for the carbon NMR, here we have carbon here. Okay, we call that carbon. Let's label it C. Okay, which is the same as this carbon here, C. So we have carbon A, B, C. For the C NMR, we have 3 signals. I hope that makes sense.